slide.
You can. All right, so we're live. Let me just get confirmation from the chat to see if people can see us and hear us well. I'm seeing comments on YouTube, and I think we're good on LinkedIn as well. Okay, awesome. So we're getting confirmation that that we're live. So this is the first of our Learning Together series, and I'm pretty excited about this one, actually. This is going to be a series of experts in their fields that we're inviting over to give talks on interesting topics, everything from language models to RAG to agents. And in this one is interesting because it touches pretty much all of what we've talked about: RAG, language models, quantization, agents. I'm really happy to have Aditya here, who's the inventor of one of the inventors of Matryoshka machine learning, and he's going to touch on a lot of his recent works. And the really interesting thing about this technology is that if you've built a RAG system, if you've used a language model, probably a part of your stack is already using some of the technology that that he's been pivotal in creating. So maybe we can we'll wait a couple of minutes here, and then I can hand it over to Aditya, and then we can get started. Aditya, do you know if your slides will be available to listeners afterwards, or?
I need to double check, but yeah, I mean, it's going to be anyway recorded, right? So
Yes, it'll be recorded and it'll be up on YouTube. So. All right. So what I'll do is when Aditya is presenting, I'll go off stage, I'll bring his slides on, and then if people have questions, you can type them up in the YouTube comments and in the chat. And Aditya has mentioned that he'll be happy to take them during the talk, and we can take whatever's left after the talk as well. Awesome. So Aditya, let me bring up your slides, and then you can get started whenever you'd like.
yeah, seems like I can't change the slides from here. So
yeah. So if you go,
Okay.
to your, is this on Google Slides?
Yeah.
Yeah. So if you just go to the go to your Google Slides where you're sharing your screen from, and if you just flip on those, it should be. Yeah, I can see it changing there. Okay.
Yeah. Cool. Yeah. Thanks everyone for being here. Thanks, Zain. I met Zain about a year ago when some of these works became mainstream and they were looking at understanding it better. I'm happy to be here, happy to take questions in the between. So if there is anything that's not clear, yeah, and there are logical breakpoints. So yeah, having said that, hi, I'm Aditya. I'm a researcher at Google DeepMind. I did my PhD from University of Washington about 9 months ago. Most of the work you see here is a joint work during my PhD and what I'm been up to here at DeepMind. So yeah, I mean, it seems like it's a bit of a philosophical thing I'm pitching here, Matryoshka principles for adaptive intelligence. There will be decent low-level details, but the primary goal of this talk is to show the generality of this simple technique across a bunch of uh, very important fundamental aspects in our current deep learning pipelines. Cool. So let's get started. Uh, to just motivate why there is a need for this, all of this stack to be adaptive. One thing we keep forgetting is our downstream needs and deployment settings keep changing every single time, depending on the task, depending on the user workloads, etc., and etc. And you cannot account for everything with a single rigid design. Like, I mean, like you can probably like account for like 80% of the traffic, but you cannot account for every single thing. And last thing is, if you bring this adaptivity into the fundamental machine learning blocks, my thesis was that we should be able to make any system which is in current deployment to be adaptive to ever changing scenarios. And that's the major goal of making these things adaptive. So let's take a very basic example of a deep learning fundamental building block, which is a vector representation. So when I say a vector representation, it's also called an embedding most of the times. That is when a data point or an image like this dog goes into a neural network. It is converted to a d-dimensional dense vector. Let's say it's a 128 dimension embedding, and yeah, this is what we see. Like this is like Google's Gemini embeddings, Cohere's embeddings, OpenAI, a bunch of the most popular APIs on open source, Hugging Face, etc. They all let you do this. And yeah, I mean, when I started my PhD, the neural network was a ResNet 50, and we used to just like process the images and like assume that this was a good enough feature for us to build all the downstream tasks on. However, when you look at these downstream tasks or like try to do fine tuning on top of this for transfer learning, you have certain applications which are latency sensitive, like search and object detection, which are very, very dependent on the dimensionality of the embedding. So if you increase the dimensionality of the embedding, your latency is going to increase. So especially in case of search, if you go from 64 dimensions to 128 dimensions, regardless of how good your data structures are, there is a dependence, linear dependence on the dimensionality of your embedding, and doubling the embedding increases the latency by 2x. And then there are the other set of tasks on the other side, like accuracy driven, like something like classification. It might be the case that 64 dimensions and 128 dimensions really do not change your latency for classification, but going from 64 to 128 increases your classification performance by 3%. However, if you're going to use this constant universal backbone for all of your applications downstream, because these neural networks are super expensive to deploy everywhere, uh, you're going to have to make a trade-off, and it's either going to be latency sensitivity or accuracy driven. So if you make search your primary citizen, your classification becomes a bit under represented, and you lose that 2% you could have gotten from 128 dimensions. So doing any of this trading off or like doing post hoc compression either loses on accuracy or not fully adaptive, because it's not like natively adaptive. You need to like actually think about every single scenario and make things that work for it. So this was the primary motivation when I started off working on this line of work. And the first thing we came up with is this thing called Matryoshka vector representation, or Matryoshka embeddings. So the idea is pretty simple. It's the same embedding which we have gotten from the previous pipeline, which is a dog going into a neural network and embedding. But right now, instead of just having a 128 dimension embedding, I'm going to say that the first 16 dimensions is going to contain the most important part of this data point. And the first 32 dimensions, which has the first 16 dimensions as the as part of it or nested within it, has the next important. 64 has the 32, which has 16 inside as the next important, and 128. If you look at this, this reminds you of a Russian nested doll. That's why the name Matryoshka. Matryoshka means the Russian nested doll, where you see that the largest doll and the smallest doll have a lot of things in common. But as you increase in size, the details become more and more profound. And as you decrease in size, you actually do not care about details. But you are able to make out what the doll actually stands for. Cool. You can use this first 32 dimensions after you have the structure for retrieval, and you can use the full 128 dimensions for classification. Okay. So just to reiterate, now the representation or the embedding is a 128 dimensional dense embedding, which has the most important information in the first 16 dimensions, followed by first 32, 64, and so on. So if you want a 16 dimension embedding, you just take the first 16 coordinates of your 128 dimensional vector, and you should be good. And I'm going to claim that this is accurate and adaptive, and we argue about this with a lot of results and deployments in the next couple of slides. Cool. Yeah, a constant question which comes to me whenever I present this is, how do you ensure that this happens? Is there some magic trick? And it turns out it's actually very, very simple. The idea is extremely simple. Instead of training your embedding model with contrastive or softmax loss on 128 dimensions, you do the same loss on the first 16, first 32, first 64, and 128 dimensions. So you just take all these losses and jointly train them. That's pretty much it. Okay. If you look at it closely, at least in this case for Matryoshka representation learning, all of the compute can be reused. That is, whatever you computed for 16 dimensions is already part of the first 32 dimensions. So you can just compute the next 16 dimensions of the 32 dimensions and just add them up. So technically, for the same cost of training a 128 dimension embedding, you are able to like nest all of these things and get it to work. So in short, it's doing the same learning task. It can be contrastive, it can be mass language modeling, next word prediction, whatever you want to do, at exponentially separated granularities in this information bottleneck, which is an embedding. Cool. So the mental model I want all of you to have for looking at this data, how do we look at the representation of the data, is that, let's say you have this dog and there is a 128 dimension embedding which is representing the dog. The 16 dimensions contains all the blurry features. It helps you understand if it's a dog versus a cat. Probably nothing more than that. As you increase to 32 dimensions, the higher details come into picture. 64 more, and 128, you probably have a perfect reconstruction. This is not exactly how it happens when you take a ResNet 50, but if you actually go for like more reconstructive and generative models, you can actually see this happening. And quick results to convince most of you that like this works. So we have trained a ResNet 50 baseline on ImageNet for varying embedding sizes. So each of this red point is a different embedding size, 8, 16, 32, and so on until 2048. And y-axis is one nearest neighbor accuracy. You can think of it as a proxy for your classification accuracy, but it's also a proxy for how good your search quality is. And each of this red point is independently trained. So I had to train a different model for each of these things. And let's say each of them takes 3 hours to train. I actually have 9 times 3 worth of compute here. And the orange curve you see is taking the 2048 dimensional representation and doing PCA or SPD on top of it. It kind of holds up very well until 128 dimensions, and after that it just drops off drastically. So post-hoc compression works very well for certain ranges, but if you go to something much, much lower, it just falls off. And from a search perspective, if you have your document embeddings in your database already encoded, if you want to do any of the post-hoc compression, you have to re-encode everything. And it's a pretty expensive process. In contrast, Matryoshka representation learning, or MRL, is this one blue curve, which has all these embeddings as part of one single training run. And you can literally pick any of these dimensionalities, and they're as good, if not better, than the corresponding baseline. Okay, so this is just one 3-hour run, and every single one of them falls on the Pareto curve. So a takeaway here is Matryoshka representations are as good as constraint-specific baselines, if not significantly better than post-hoc compression. And the most interesting result for me when we came up with this paper was this granular interpolation. So what I mean by that is we only trained our model for 8, 16, 32, 64, 128. But someone comes to me and says, hey, Aditya, I can afford 48 dimensions, but like you're only giving me a 32 dimensions. What do I do? The answer to that, surprisingly, is you don't need to do anything new. You just literally go and like pick the first 48 dimensions, and it interpolates extremely smoothly between 32 and 64. It was never trained for, but this interpolates completely accurately being on the Pareto. And this allows you to span the entire Pareto extremely densely, which was not possible before. Cool. So a takeaway from all of this about Matryoshka representation learning is you just need the first k coordinates or dimensions to give extremely accurate low dimension embeddings. They're as good, if not better, than training things from scratch. They're agnostic to scale and modalities and representation learning setup. It scales up to like billions of data points very easily. It works for text, image, audio, everything you want to do, different representation learning setups. And lastly, of course, like the whole goal of this was enabling task aware and adaptive fine grained deployment, and that happens. We came up with this paper about 3 years ago, but people have only realized the potential in the last year or so. Most importantly, most of the day-to-day search tasks you have on Google, Pinterest, any of these things are powered by Matryoshka representations. Every single API provider who has an embedding endpoint has Matryoshka representations to allow for flexibility on the fly. And currently it's serving over a billion users daily. And yeah, like as Zain said, if you're using a RAG pipeline, you most likely are touching some part of Matryoshka representations. It's not just industry labs and APIs which embrace this. We had extreme amounts of love and support from open source community. And when this came out, when this became popular last year, currently about 10% of Hugging Face model downloads have Matryoshka representation learning, which is like insane. And yeah, I mean, it shows that like people, both the designers want to have this elasticity and the developers want to use it for whatever task aware and adaptivity they care about. Any questions here? Okay, seems like, okay, I'm not sure. Okay. Yeah, I mean, if any of you have any questions here, we can.
Yeah, there's no questions so far. So I'm going through the questions. If people have questions, I can bring them up
Okay,
whenever you'd like.
thank you. Cool. Yeah. So that's pretty much it. Like that's the basic idea of Matryoshka representation. So the idea is like do the same thing at multiple granularities, and voila, you can just like smoothly interpolate between every single thing in between. After the paper came out, we actually found that people in academia figured out more interesting things to do with this. So the notion of Matryoshka is just not an input space, but also in output space, but also in input space. So Lucas Bayer and co figured out how to do elasticity for patches. So if you are able to do 196 patches, you should be able to do it. But if you're only able to process 14 patches, you should also be able to do it. So this elasticity was brought to input dimensions through this thing called FlexiVit, and it works really, really well. And all the observations we have in output space translate to input space. And then more recently, people figured out this can be done on token space for lava-like models. So when you're processing images, you can actually afford to process only a portion of them, or like only give portion of the tokens to your language models, and that reduces your prefill cost and your context length significantly while not losing out on any accuracy. People also figured out adaptive token representations where you can incrementally keep adding details as you need, depending on how much processing you want on the fly. This was something which came out of nowhere, and I never expected this. Was people found extremely good use case for sparse autoencoders for mechanistic interpretability by adding Matryoshka. They were able to fix a bunch of collapsing problems by adding this simple nested structure, and yeah, it turns out like it makes things a bit more stabler than what things were before. Of course, like this is very applicable to unit style generative models where you have different different amount of compute for your generation and different resolutions you care about. It's not just useful for diffusion models, but also can be used for VAEs in adaptive compression. So yeah, like go check these papers out. Like they're really, really cool in the last few months. Yeah.
We do have a couple of questions on MRL if you'd like to take them now.
Yeah, that would be great. Thank you.
Awesome. So this question is, I think, is asking if one model provides all of these embeddings or if these are different models that are providing these embeddings.
So in Matryoshka representation learning, the blue plot, it's one model which provides everything. The red things are 9 different models.
Okay. And then the next question here Is there any downside to doing MRL? Why would you not do MRL?
Exactly, that's the whole point. You should never not do MRL. So
Yeah, exactly. That's the greatest part of this. Awesome. Thank you.
okay, I can move on to the next part, I guess. So when we did the representation learning part, people asked this question: can this be applicable to every single part of the transformer? And yeah, I mean, like, it sounds logical, right? It's the fundamental building block is a dense vector in most of these cases, so you should be able to do something. So we started looking at it. Especially, we looked at feed forward part, the FFN or MLP part of transformer, which literally has a dense embedding in the bottleneck, where you have an up projection and a down projection, and everything in between is a hidden network, a hidden dense vector. So yeah, I mean, let's make transformer elastic, and it's very, very straightforward. And we call this Matryoshka transformer. It was published in Europe 24. So we just bring the Matryoshka structure into the FFN of transformer. So you have, let's say, your FFN dimension is like 1024. You have the granularities of 512, 256, and 128. Let's call them S, M, L, and XL. And yeah, this is exponentially separated granularities. And this just brings the structure to transformer. We call this modified transformer block as matformer block. It's short for Matryoshka transformer. Cool. So the same way you can build a transformer model by stacking multiple transformer blocks, you can also stack multiple matformer blocks to make a matformer model. And this allows you for a lot of cool elastic and adaptive things down the line. So the way you train it is very similar to what we did for Matryoshka representation learning. Is uh, in your matformer model, take all the layers with the smallest granularity, stack them up. That becomes your small model or model S. The medium granularities, it becomes model M, large model L, and extra large is model XL. So for the same batch of data, you let the batch of data pass through each of these models and compute loss, and you jointly train them. That's pretty much it. Okay. One thing to note here is, unlike Matryoshka representation learning, this compute is not reusable because there are non-linearities in between. So a model S, model M, model L, model XL, while sharing the weights, do not completely share the compute. So when you're training these things, it's going to be a bit more expensive than training just the largest model or your base transformer model. Okay. How expensive? It's going to be much cheaper than training each of these models separately because of the shared structure. It's going to be about 30% overhead on top of your largest model. So let's say you take 100 GPU hours to train your largest model, you'll be spending 130 hours of GPU. But if you are like not doing Matformer, you'll probably be spending close to like 180 to 200 hours to train all these four models together. Okay, now that we train these models, we get Model S, Model M, Model L, and Model XL. They're pretty good for a lot of these use cases. And if you recall, we were doing Matryoshka representation and we had this granular interpolation come for free. So things were very smoothly interpolating on the Pareto. So I wanted to see if we can actually find some models in between to cater to these personalized devices because of their like deployment constraints. And it turns out the answer is yes. And you should be able to find an extremely densely spanning Pareto by doing this thing called mix and match, where you should be able to change the granularity of a layer in a given transformer model. So let's say you have 10 layers. You can use the first layer to be full XL, second layer to be M, third layer to be S, and so on. If you notice, this becomes combinatorially large, and you should be able to span all the points in between model S, model M, model L, and model XL while being on the Pareto of accuracy frontier. And if you do it right, and if you search for these things, and this is all without training, this is all after the training, so this is all for free during inference, you should be able to get hundreds of free compute adaptive models in one single shot. To convince you that like this works, it's the same plot. Like each of the red baselines is four different models on VITL for this one for trained on ImageNet, and the blue one is a matformer model. So each of them is as good, if not better, than your baseline. And now the most interesting part is, despite optimizing only for these four parameter configs, all the stars are mix and match. Like they're all for free. We never trained for them, but you got all of these 100 plus models for free. So I sampled a bunch of them to make it easier. But when you sample everything, it falls into the convex hull, and quite a few of them lie on the Pareto, which you can just pick up and use. Cool. So it's not just for VITs, it works for language models extremely well. So when you do scaling laws for like baseline models and like matformers, they pretty much align. And this is not accounting for all the 100 plus free models you get downstream. So even without that, when you're only looking at the base models and the base granularities, everything just works out as if it's a regular transformer just scaling well. We figured out this matformer idea is very general. It works for MLP hidden dimension. That's what we started with. And then people in NVIDIA figured out to extend it to depth, attention, and model representation. You should also be able to fit a router on top. We have some follow-up work on how to use conditional compute on the fly. So in short, this is applicable to every single transformer components. And yeah, it's a very general purpose technique to make a given transformer based model elastic. Any questions here?
We do have one question here that's
How are the first k dimensions ranked to be so influential on the accuracy? When the features are randomly ordered, why would the most influence come from the last k dimensions? Hi, I think this is more in relation with MRL. We are training the first k dimensions to have a loss, and so on, right? So if you think, let's just look at the first 16 dimensions in the case of MRL. It's actually getting gradients from 16 dimensions, 32 dimensions, 64, and 128. So even if you're only training for 16 dimensions once, you are actually getting gradient 4 times. So it becomes the most important 16 dimensions there is. So you can actually take, let's say, OpenAI's text embeddings or Gemini embeddings, try to find the most optimal 768 dimensions. And I think it's always going to be the first 768 because they're all trained with Matryoshka.
it's interesting. If you look at the variance or the standard deviation of these embeddings, you can actually um, see the structure that they use to train it. So I think it goes like 768 and then the next 768, and you can see it as a stepwise function.
Yeah.
Pretty cool.
So I think Zain tweeted this out. I think someone else figured it out. But yeah, when you plot the variances, it's very, very clear that the variances are pretty distinct. And yeah.
Yeah.
Yeah, and I think Mosul had a question. Matformer seems like a MOE-like structure. Yes, that's a very astute observation. It is an MOE-like structure where the smallest granularity is the most important one, and then you only incrementally can route to the rest of the parts based on what you need. Flextron is a great paper to read if you want to look at this. And yeah, I mean, you can see how people learn routers on top of it. In our line of work, we have something called mixture of nested experts, which also does something very similar to Flextron. So yeah, that's quite useful. Any other questions?
Oh, I think we're good to go.
I mean, I think we are done with Matformer. So in case anything else is there, otherwise I'll move to the next part of the talk. Cool. Okay. So let's move to something a bit more different. So until now, we worked on the dense representations, and then we extended to transformer. But then um, we had an interesting question to ask, like how far can we push this Matryoshka idea? And yeah, and that resulted in something called Matryoshka quantization, which is published in ICM in 2025. So I'll present about that, and this is the latest work in the entire Matryoshka line of work. So in case we want to quantize something like a Jama2 9B model, you're going to take a Jama2 model, either do uh, post-training quantization, which is on the fly without any training data, or you can afford to do something like quantization await training or QAT. During that process, during QAT, you try to minimize the loss with 8 bits such that you find the most optimal scaling parameters for your quantization to work. However, let's say the application like Google Firebase has extremely high server load. It wants to, on the fly, use an int4 model or an int2 model. But in order to get these models, PTQ works fine for Int4, but for Int2, it really does not work really great. You have to optimize with quantization aware training, and this requires you to train multiple models. So you have to train a model for 8-bit, 4-bit, and 2-bit. And you also have to save these models because they're all differently trained and they have different weight distributions. So you have to serve these three models separately. So despite you trying to save on compute, your memory is going to blow up. So one solution which a lot of us have is quantizing models on the fly, which is post-training quantization. Uh, but the thing is, baseline is a quantization aware training thing, the red one, and the orange and green are on-the-fly quantizations. And on-the-fly quantization for low precision is pretty less accurate. At the same time, for the baseline QAT, you have to train for each of these things separately. So there are like 5 different points: 8-bit, 6-bit, 4-bit, 3-bit, and 2-bit. You have to train for each of these things separately. And it's expensive. It's also expensive to store. So, yeah, that's the problem. So, that's where we came up with the idea of Matryoshka quantization. And the idea is very simple. If you actually look at an integer data type of 8 bits, the first 2 bits actually correspond to a 2-bit quantized version in some notion. And the first 4 bits correspond to the 4-bit quantization in some notion. Okay. So if you learn your weights of 8-bit correctly, you should be able to do a 4-bit quantization by taking the first 4 bits. And if you are able to do the entire thing right, your first 2 bits should also correspond to a 2-bit quantization. So the easiest way for you to think about this is an 8-bit representation with like first binary code being 1 and everything else to be 0 corresponds to 32. 32? Oh no, 64. And if you slice off the first 4 bits, the value becomes 8. That's it, right? And it becomes 8, and 8 is actually just division of 32 by 4, showing that, 64 by 16, that is shifting things by 4 bits. So taking this idea, we wanted to show that when you're optimizing for 8-bit quantization aware training, if you optimize for 4 bits and 2 bits, you actually see this Matryoshka structure come out, and you can jointly optimize these things together. Okay. And it turns out by doing this, the blue plot is MatQuant or Matryoshka quantization. We only train for 8-bit, 4-bit, and 2-bit. It's as good as the baseline, which is independently trained. But also, the 6-bit and 3-bit were never trained for, and they interpolate smoothly and they're as accurate as an independently trained baseline. Further, the 2-bit accuracy here improves by 3% just because of the better optimization dynamics. We also have seen this in Matryoshka representation learning, where lower dimensionalities start improving in accuracy more than the higher dimensional representations. So what is happening at a high level hand wavy things is we notice that when you are actually learning only int 8 in your QAT, that's the red plot. It does not have any incentive to actually optimize for int 4 or int 2. So it just like learns a good Gaussian distribution. However, when you look at int 8 trained with MatQuant, it pushes the values to the right. So what it means to push values to the right is the magnitudes go up. It will not affect the quality of an int 8 model, but it affects the quality of an int 4 and int 2 model significantly because now they can afford to use more buckets than they were able to use before. Okay. A very simple way of thinking about this is if a value is 31, if a value is 64 or 65, it does not matter to int 8. But if a value is 16 or 17 matters, 15 or 16 matters a lot to int 4. And that is what is shown here in terms of distributions. And just by optimizing and making 8-bit be aware that there exists an int 2 inside, you improve the int 2 quality significantly. Cool. So the same ideas as Matformer are applicable here. You should be able to do different precisions across different layers, and you can span the entire thing Pareto optimally, near Pareto optimally, and all the stars are for free. So you can just like pick the first few layers to be in 2-bit, next few layers in 4, and next in 8, and go back to 4 and 2. And that's always Pareto optimal. However, if you notice, the 3-bit interpolated number, the round, is much better than the stars. And we wanted to investigate what happened here, and we realized that outliers play a huge role. And in order to make all of this Pareto optimal, we had to store 2 to 5% of all of the weights in an extra bit. So what we mean by this is, if you have a 2-bit quantization, we are going to store 95% of the weights in 2 bits, but we are going to store about like 2 to 5% of them in an extra third bit, and that helps us move everything beyond and make it Pareto optimal. And this is not a new thing. Like Tim Detmers and Bits and Bytes, all of these people figured out that like outliers are quite important, so storing them in a different precision is quite useful. But the surprising thing is, storing this one extra bit for 2-bit improves accuracies by 8%, and this is quite uh, uh, interesting, because this now makes 2-bit a viable contender to be an optimal quantized model for downstream deployments. We also found further improvements. We found that the training is stable and like increases further in accuracy when we are doing QAT in MatQuant using co-distillation between int8 and int2. So because int8 and int2 are in shared space, we want to use the int8's logits to also supervise int2. So that improves things quite a bit. So the 8% you see includes this 4% improvement, and then the 3%, and then the 1% from the outliers. Further, we noticed that we can use this simple idea to stabilize attention quantization as well, which was unstable to directly do. Usually, FFN is what we quantize in most of the open source models, and it turns out you can stabilize all of these things by a very weird variant of MatQuant, where you have an 8-bit quantized integer, but you only optimize for 2 bits. So you have extra bits to move around. So it's like over parameterization. So you're flipping around more bits, but your loss is only coming from 2 bits. And it turns out this just stabilizes quite a bit, and your 2-bit improves further than MatQuant. However, the trade-off here is your 4-bit and 8-bit are going to be extremely bad because we are never optimizing for them. But if you only care about 2-bit, this is something which you should be looking at. So a further set of steps here is, we wanted to initially extend this to floating point 8 and floating point 4, similar to int 4 and int 8. But it's not very straightforward because ints are linear in scaling and floats are exponential. It's pretty hard. So if any of you have any thoughts, happy to chat more. And we also want to train a router on top of entire MatQuant to load the quantization which we care about dynamically from our HBM or GPU RAM into SRAM, and to improve the speedups further. Yeah, I mean, any questions on MatQuant here? I'm happy to take. We are almost out of slides, so yeah.
So I think this one is not specifically MatQuant, but it might be Matformer here.
If interpolation between Matryoshka layers is so smooth, how do you determine optimize for how many layers is best? That's a good question. Because this is not training intensive, it's all during inference. Usually, we start playing with some configurations on a downstream tasks, and we get a feel of what layers are important for these tasks, and we can just start optimizing around it. It's like neural architecture search, but there is no training after the search. You can directly use the model on the fly. Um, there are some heuristics we follow. Like in MatQuant, we talked about pyramidal, where we start with lower precision and then go to higher and then go back to lower. We see quite a few of these heuristics work really, really well, but it is dependent on the task, and it's good to like sample a couple of points on the parameter configs you care about, and then pick the best ones on the Pareto, closest to the Pareto.
There's also another question here if you want to take this now.
Yeah. We're working on a runtime that snapshots full model execution state, KV cache attention memory layout, and restores it directly to the GPU to enable instant cold starts. Curious how your nested Matryoshka approach could intersect with snapshotting. Do you see a path where model compression could dynamically prepare restoration to scale up and down across agent workflows? That's a good question. Um, if you're bottlenecked by how much state you can preserve, you should be able to do very accurate 2-bit or 4-bit with mat quantish stuff or Matryoshka. So your prefill, like let's say like you have hit like 100,000 context length at this point. Maybe some of these things are not as useful. Probably you can just like make them all store in lower precision, be it Matryoshka or mat quant, and you can afford to store those things because you probably still care about the information, but you probably don't need them fully. So that's the way I would think about it. uh, yeah.
Awesome. I think that's all the questions we had for now.
Okay, so the final slide is takeaways. The principle of Matryoshka generalizes extremely well across fundamental blocks of machine learning. It's not just the representation learning, transformer, and quantization I showed. People have done this for tokenization, people have done this for reconstruction, generation. Yeah, most of the stuff which we have right now, which involves learning, can be made Matryoshka. And the models are decently over parameterized that this inductive bias actually doesn't end up affecting how things are done and how the accuracy scale. Second thing is elasticity and adaptivity eventually will be extremely, I mean, it's already being in use, but eventually as we scale the models even further, will be extremely crucial to developing real world AI, where you should be able to deploy the same system starting from a mobile phone to hundreds of thousands of GPUs on the fly. Last thing, if there is one thing I want all of you to take away from this, is this works. It's extremely simple. It's as good as like 4 lines of for loop for most of the initial prototyping. Extremely scalable. Just go and use it. Let me know how it works. And that's pretty much it from my side.
Awesome. Thank you so much. So let's see. Now we can open it up to any more questions if people have. I have some questions that I can ask as well. So thank you for the awesome presentation. The first time I kind of spoke to you, you were explaining Matryoshka for embedding models, and now there's the Matryoshka transformer as well as MadQuant. So it's interesting to see how generally applicable this is, and other people building on top of that as well. So it's awesome.
Yeah. I mean, I was surprised by the amount of generality as well. I mean, it's not like we discovered it first in 2014. Oren Ripple and co figured this out. They called it nested dropout, but their use case was about adaptive compression for reconstruction models. Then slimmable networks were a big thing in 2018, 2019, where people wanted to have elastic CNNs. They worked really well. However, like I think being able to do this for transformers at scale was quite useful, and like we noticed that there was some engineering challenges we had to overcome. So so that just made it much more generalizable in the current landscape. But from the representation learning perspective, all the experiments we have ever run on were images primarily, and it was very surprising when all the industry and open source scaled it up to language and like showed text embeddings work as well. That was really interesting as well.
I wonder if there's more explainability work around. So you showed that slide of a dog, and then if you take the first 16 dimensions of the embedding versus 32 versus 64, you get the first 16 capturing like a fuzzy representation. You can tell that it's a dog, but maybe you don't pick out the details. Is there any explainability work that's done on language Matryoshka vectors, and what does explainability look like in that domain?
So SAEs is the are the closest I would say, but again, like they're not exactly interpreting the exact representations. They're trying to understand the internal activations, etc. So that's where they try to organize information such that the most important concepts are captured earlier and like most frequent ones, and you can build a nice semantic tree of sorts. Um, I mean, it's one thing to note is I never thought of this to be used for interpretability, and that was very surprising to see it's useful.
Mm-hmm.
And people also talk about this as a hierarchical representation.
Yeah.
When we initially were writing it, we never thought about it that way, but turns out it's quite useful tool to think about it as a hierarchical representation.
Yeah, that makes sense. That's how I think about it in my mind as well. Like just loading up more important pieces of information in the earlier dimensions. Um, I guess the other thing you mentioned that 10% of all models on Hugging Face use MRL now. I'm wondering because when I read the initial paper, it said that you can take any non-MRL model and you can turn it into a MRL model by fine tuning it. So is there, if I take a pre-trained not MRL model and I fine tune it into an MRL model, is there any difference between that model versus it just training from scratch in MRL? Is one better than the other?
So in MRL, slightly more data is better. If you can, it's again, it depends. Like if you have a 2048 dimensional representation, if you want to go to 64 dimensions, fine tuning is probably not going to be your best friend.
Yeah.
Training from scratches, but going from 2048 to 512, probably it's pretty straightforward. The same principles apply for Matformer style stuff. Like Flextron is a fine-tuned version on top
Mhm.
of an existing pre-trained model, and it does really well. But you can actually further improve it if you want to do things from pre-training.
There's one question from the audience here that we can take.
Yeah. To allow a continuously decreasing order of importance to bits in the embedding, would a loss function that gives exponentially lower weight to bits depend on index allow for this continuum? That's a good question. We actually thought about this, but it turns out when you have the embedding to be a float number, whatever weight you give will be absorbed. So let's say you have only 4 dimensions and you're going to weight the first dimension by 4 times. The floating point number in the first dimension will just reduce itself by 1 by fourth. So everything just goes to the same scale. So you need to have a different way of doing this. Yes, you can reweight things, but reweighting can just like collapse things if done not right. But this is a very, very good question. It also destabilizes training. If you do exponentially large stuff, at some point of time, it will just start destabilizing the training. But this is an interesting thing. You should try this out. But yeah, I mean, when I tried, like this is what my understanding was.
Awesome. You also mentioned for Matformer, you can have mix and match where you can have maybe the first uh, feed forward hidden dimension be higher dimensionality and following ones be lower. Um, when you ran experiments, did you find that there was like some understanding of make the earlier layers higher dimensionality and then the future ones can be lower layer? Or is there any kind of intuition around that?
Yeah, I mean, we also initially thought that initial layers would be more precision and later higher precision, but I think the other one lower precision but it turns out like experiment showed us the other way around. So we want lower precision in the initial layers and like higher precision later. It's probably something to do with residual connections and you're adding more compute and like representation as you go along. It was a bit interesting, but it also depends on downstream tasks. So it's very subjective to yeah, so the task at hand.
Sounds good. Let's see if there's any more questions. And yeah, I'm not seeing any other questions. If people want to reach out to you or if they have any questions, how can they reach out?
Yeah, I mean, they can reach out to me. I think my website has my email, so like the website should be able to help you point you to. But yeah, most of the code base, etc., should be available linked to the code papers. But most of them are pretty straightforward to implement. So yeah, give it a shot.
Awesome. Thank you so much. So I think we have no more questions. We're gonna end it off here. I want to thank you for coming on, and this was an awesome kind of whirlwind of this technology that goes on underneath the tools that we're using. Um, yeah, thank you so much.
Yeah, thanks a lot, everyone.
Thanks everybody. Take care. Bye.